Swayam Prabha. Digital India. Educated India.
So, during my last lecture I have discussed about the Mehrop equation, then Henson and basic bearing capacity equations, and then for eccentric loading what are the conditions as per different theories, those are also discussed. Now, today's class I will first discuss about the IS code recommendation, then I will solve a few example problems. So, like previous different bearing capacity theories, IS code also has recommended bearing capacity equation by which we can determine the net ultimate bearing capacity. Okay. So, this is the equation which is similar to the general equation that we have discussed. Here also SC, DC, IC, that means the shape factor, depth factor, inclination factor, those are proposed, and the NC, NQ, N gamma values are similar to the values proposed by basic we have to use. So, basic table we have to use for the for N gamma calculation, and for basic also NC and NQ are similar to Mehrop bearing capacity factor. So, and then there is a term W here, water effect is also incorporated into the equation, but in previous equations the water table effect we have to incorporate by using the equation those I have given or I have explained during the Tarzaki's bearing capacity equation. So, I have already discussed the Tarzaki bearing capacity equation, and then I have also discussed that how we can incorporate the water table effect in that equation. The same way the water table effect can be incorporated to others bearing capacity theory also. Okay. So, that means in Mehrop, Henson or basic we can incorporate the similar way the water table effect into those theories, but the IS code has given directly a water table effect in its equation. So, as per IS code we have to use that, and remember that in other bearing capacity equation the net ultimate bearing capacity is given ultimate minus gamma df. Okay. But here that gamma df part actually, so we know that here q or q0 is gamma df. Okay. So, here that part is incorporated here. So, that means you can see that this is q into gamma df. So, that means which is subtractive, which is okay, that we have to subtract that gamma df to calculate the net ultimate bearing capacity. But again you can see that all these SQ is DQ, IQ terms are also included into that subtraction. Okay. So, that is the difference because other cases we first calculate the ultimate bearing capacity and then we subtract gamma df to get the net ultimate bearing capacity. Okay. But in IS code directly we will use the net ultimate bearing capacity by using these equations, and where water table effect is also incorporated. But others equation water table effect also we can incorporate by using the equation or the procedure that I have discussed in my previous lectures. So, where the water table effect is there. So, water table effect W value 1 when water table is at or below the depth okay, depth of below the depth of df by b. So, that means it is same as the previous water table effect, that if the water table is below the depth which is equal to the width of the foundation from the base of the footing, then no water table effect will be there. So, for example, that if this is my foundation, okay, now this is the B, and if water table is effect is water table is here and this depth is greater than B, then water table effect will not be considered. Okay. But even if it is equal to 1, then the W dash value will be 1. So, that means basically there is no water table effect. 1 means no reduction, nothing. So, that means water table will play a role into the bearing capacity equation if this position of the water table within width of the footing from the base of the footing. So, that means if it is within this zone and above base of the foundation and above the foundation, then the water table will play a role. Okay. Now, W dash is 0.5 when water table is located at a depth df or likely to rise to the base of the footing or above. So, that means here it is mentioned as per IS code that if water table is at the base of the footing, then W dash will be 0.5 and here W dash equal to 1. So, that means if water table is within the water table position is within ground surface and base of the footing, then the W dash value will be 0.5 as per this recommendation. So, that means is water table as the base of the foundation or above, then the W dash value is 0.5. That means, if the water table is at the surface, that is also 0.5, and if the water table at the base of the footing, then also 0.5. Okay? And we can linearly interpolate the value of W dash in between these two base and at a distance of B below the base of the foundation, we can linearly interpolate. Q is the effective pressure at the base, and remember that when we use the Q, definitely it is effective, okay, because in other case we incorporate the water table effect, here it is Q is given. So, that means here W dash is applied at the third term, but the second term also we have to apply the water table effect. So, that means suppose if your water table at the base of the foundation, then your Q will be simply Q bulk into gamma df. Okay. Bulk means the above the water table, okay, unit weight. But if your water table at the surface, then Q will be at Q sub into df. Okay. So, now this is your if water table at the ground level, and Q sub gamma sub is equal to gamma sat minus gamma W. Gamma W is the unit weight of the water, and if it is at the base of the foundation, then this will be gamma bulk. So, gamma sub is the gamma sat is the saturated unit weight, gamma sub is the submerged unit weight. So, that we have to use soil below the water, and gamma bulk is the bulk unit weight, that we have to use soil above water table. Okay. So, now if the water table in between that, so suppose your water table is here. So, as per our IS recommendation, if water table is within the base and the ground surface, then W dash will be always 0.5, but Q value will be here. So, suppose this distance is say A, and this is gamma df, and then in such case your q will be gamma bulk into A plus gamma sub into df minus A. Clear? Because we have to consider the effective pressure at the base. Okay, so that means what is the effective pressure? We have to consider effective overburden pressure at the base. So surcharge will be always effective, and this is the way we can incorporate the water table effect in the both the terms, the first term as well as the second terms as well as the third term also. Okay, but in others theory you can use the procedure that I have discussed, which is also similar to the this type, which is a slight variation, because but the similar way also you can determine the, you can include the water table effect in the bearing capacity equation, as I have discussed during the Tazakis bearing capacity equation. Okay. So, now we can as I mentioned that we have to linearly interpolate the value if the water table is from the base to a depth of b, then we have to linearly interpolate from 1 to 0.5. So, you or we can use this chart also. Okay. So, suppose if what is the d, and so this is your foundation, this is the base, this is the depth of foundation, and say suppose this is the distance b, width of the foundation is b, and water table position is here, say. That depth is a small d from the base of the foundation. Okay. So, now if d by b is equal to 1, that means d is equal to b, that means your water table at a depth of b from the base of the foundation, then definitely W dash will be 1, because we know W dash is equal to 1 here, and at this position W dash equal to 0.5. Now, if d is equal to 0, that means at the base of the foundation water table position, then the W dash value will be 0.5. In between that we can use this chart. Suppose your d by, so that means d by b will vary from 0 to 1. So, this will vary from 0 to 1, then for 0 it is 0.5, for 1 it is 1. Okay. So, in between that we can use this chart, or you can linearly interpolate the value also. So, you can use this chart also to calculate the W dash, and then others factor you will get for bearing capacity factor same as basic, and gamma df as I mentioned, if this is effective, always effective. Okay. And the factors, others factors, say factor, depth factor, inclination factor, you will use by using these charts. Okay. By the shape factor you will use for rectangular footing, square and circular footing, rectangular for square footing SQ, and S gamma also you will get from this table. Depth factor also I will get from this table for any phi equal to get, again it is valid if phi equal to greater than 10 degree for this equation, and the DC is varied for any phi, and dq if phi is less than 10 degree, then it is taken as a 1, and for d gamma also if less than 10 degree taken as a 1, if greater than 10 degree then this equation we can use, and inclination factor also I can use by equation using these equations. Okay. So, we will get the shape factor, depth factor, and the inclination factor. Again you remember that for eccentric loading, then one can use the IS code method with B dash and L dash to compute the shape and depth factors, and B dash in the term 0.5 gamma B dash n gamma. So, that means here like Meharov we have to use B dash and L dash to compute the depth factor and the shape factor, and in the third term we have to use B dash for in case of eccentric loading. Okay. So, now this is the first example problem, that where a rectangular footing of size 3 meter cross 6 meter is placed at a depth of 1 meter in a homogeneous sandy soil. The water table effect is not considered, because water table is at a great depth, I mean below depth of B. The unit weight of soil is 80 kilonewton per meter cube. Determine the net ultimate bearing capacity when C is equal to 0, phi is equal to 40 degree. So, phi is equal to 40 degree, that means it is a general shear failure. Okay. So, because for sandy soil, based on phi you have to judge whether there will be a general shear failure or local shear failure, or it is an intermediate state. But in case of C phi soil, based on the stress strain plot, we have to judge whether there will be a local shear failure or the general shear failure. So, in the question that will be given for C phi soil, that whether it is a local shear failure or the general shear failure, based on that you have to use the your equations. So, here it is a general shear failure and you are using the Tarzaki's theory. So, that is the expression, and it is for rectangular footing. So, these terms are also used, that is first term is not considered because C is equal to 0. So, from the table I will get NQ value n gamma for corresponding to phi equal to 40 degree, and then finally, if I put this value I will get a equation a value of 3885.12 kilonewton per meters cube. So, this is the net ultimate bearing capacity, because here this gamma d part is already taken, because here there is no shape factor, depth factor, inclination factor. So, I can write this equation in this way. So, this is the value that I am getting as per the Tarzaki's theory, because here shape factor is incorporated, because this is for rectangular footing, but the depth factor or the inclination factor, because the inclination factor will not be applied here, because it is not an inclined load is perfectly vertical and it is acting at the center. So, using Meyerhof equation, this is the equation, I will get the net ultimate bearing capacity. So, I will use these shape factor and depth factors, because I will get these things from the table that I have given for Meyerhof bearing capacity equation. I will get the NQ and N gamma value for corresponding to phi equal to 0 degree for shear general shear failure, and I will get this value for net ultimate bearing capacity as per the Meyerhof bearing capacity theory. Similar way, I will get the bearing capacity as per the Henson, because it is a very straightforward case, because loading is not inclined, it is not eccentric. So, I can use any theory, because all the theories can be applicable in this case. Okay. So, this is the value, the 3328.82 kilonewton per meter square as per the Henson's theory. Only we have to take these factors from the table, and then we will put the values and you will get the bearing capacity, and you have to select the proper bearing capacity factor corresponding to different theories. Okay. And then as per basic also I will get this value, which is 4089. I will get the SQ, S gamma, DQ, and D gamma is 1 as per the basic, as per the Henson also D gamma is 1. So, this is the bearing capacity factor, and I will get this value. Then as per IS code, here water table effect is not considered. So, W dash is taken as 1. Okay. So, so this is the bearing capacity factors, which is same as the basic, and then the shape factor and depth factor is taken from the table, and then I will get this value. So, ultimately if I summarize these values, then I will get that as this particular problem, that Meyerhof's method is given higher value, and then the Henson method is given the lowest value, but compared to other methods. but this is not I have not incorporated the Skempton's theory, because Skempton's theory is not applicable for sandy soil, it is applicable for the clayey soil. So, but it is not true for all the cases that the Meyer theory will give always higher value and the Henson's theory will give lowest value. It is not true for all the cases, because if you compare, if you look at this table here, I have taken different values and then I compare the bearing capacity equation for different theories, bearing capacity values for different theories, and you can see for phi equal to 0, that means cohesive soil, where I can use the Skempton, where the Skempton equation is given the lowest one, and other theories are more or less given the similar value. IS code and the Meyer are given the same value because their factors are similar. Then Basic and the Henson given the similar type of value, because this Basic and Henson is similar type of equation. At Azaki is given slightly higher value. But for C phi soil, when phi, this is for phi 0 and C soil, C equal to 100 kPa, for phi 0 equal to 20 degree and C equal to 50 kPa, where this case it is considered as a general shear failure, and in first case also it is considered as a general shear failure. All the three cases it is considered as a general shear failure. So, and this is C equal to 50 kPa. So, here also I will get this value, and the 40 phi equal to 40 degree and C equal to 0, here also I will get the value. So, you can see that different cases, different theories given the higher value and different highest value or lowest value. It is not that one particular theory will always give the lower value and always give the higher value. It is not the true. Even if you change the footing dimension also, then also these things will change. Okay, so that means we cannot say that which theory will always give the highest higher value and which theory will give the lower value, but it is always recommended to use at least two theories when you calculate the bearing capacity. And later on I will summarize this thing, that when we will use which theory based on the loading condition, then the others loading directions, all these things based on which theory, or the foundation or the ground condition, which theory you will use. So, later on I will discuss all these things, but right now you can say that I can say that you always use two theories to calculate the bearing capacity. Okay. So, now next part that that I will discuss, because in this advanced foundation engineering course, these are the things which are not normally not discussed in our UG level foundation engineering course or UG level core foundation engineering course, because this course is also a UG level course. UG students can take this course. So, these are that effect of soil compressibility. So, eccentrically loaded foundation, because in even for E equal to greater than B by 6 or is equal to greater than L by 6. Then foundation under inclined load. So, in our bearing capacity equation, we generally discuss that load is inclined with vertical with such angle, but we never discuss that if or load is parallel to width or length. Okay. We discuss only the loading is acting with an angle of alpha or I with vertical, but we are not bothered about the whether load is parallel to B or width or load is parallel to L or length of the foundation. But if the load is parallel to B or parallel to L, or both the horizontal load are present both parallel to H and parallel to B and parallel to L, then what will happen? How I will calculate the bearing capacity by using different theories that is also important. So, that thing will be discussed. Then most of the cases we consider foundation base is perfectly horizontal, but if foundation base is tilted one, then how we can calculate the bearing capacity. Then if foundation is on top of a slope, then how we can calculate the bearing capacity. And then very important that in our normal foundation design we take weighted average value for layered soil. Now, if the for foundation is resting on a layered soil, but in this case I will discuss the two layer soil system only. So, if foundation is resting on a two layer soil system, that means the sand above soft clay or clay above a clay, both the layers are clay, then one layer is sand, top layer is sand, bottom layer is clay, then what will happen? How we can calculate the bearing capacity? So, those things will be discussed. So, first I will discuss the effect of soil compressibility, okay, and then I will discuss about the one by one the other effects also. So, in the previous example problems I have considered the general shear failure. Okay. So, now if the soil is a local shear failure, then what will happen? Okay, that means here the phi is 22 degrees, which is less than 29 degree. So, it will be a local shear failure. Then what will happen? How we can calculate the bearing capacity? So, I have discussed as per the Tazaki's bearing capacity theories, we have to take the 2/3 of C, because here C value is 0. So, here we have to modify the phi value. So, that phi value will by using this equation, that phi dash equal to tan inverse 2/3 of tan phi. So, this is actually phi dash is equal to tan inverse 2/3 of tan phi. Okay. So, that phi originally 22 degree. So, ultimately I will get a phi dash value, sometimes it is called phi m value, which is modified is 15 degree. So, that 15 degree initially in local shear failure, general shear failure, we use the phi which is given to calculate the bearing capacity factor, but here we will not use 22 degree to calculate or to determine the bearing capacity factor. We will consider the 15 degree phi dash to determine the bearing capacity factor. So, we will from the table as per given by the Tazaki, we will get the NQ, N gamma value corresponding to phi dash, okay, and then we will get this value 121.59 kilonewton per meter square. Okay. Now, if the soil is, this is if the soil is less than 29 degree, and if the soil is greater than your 36 degree, then it will be a general shear failure. If less than 29 degree, that will be the local shear failure. Now, if the soil is within 29 and 36 degree, then how we can calculate that? Okay. So, in such case, this is the example, in such case we can determine the bearing capacity by using both the theories, that means general shear case as well as the local shear failure case. So, first what we will do, because here our phi value is given 35 degree. So, we will calculate the phi dash or phi m is given. So, same way we can calculate that phi m or phi dash, which is equal to tan inverse 2/3 of tan 35 degree, and that is coming out to be 25 degree here. Okay. So, what we will do? We will calculate the bearing capacity factor corresponding to phi m equal to 25 degree. So, that is the local shear failure consideration. So, that value is NQ is 41.4 NQ gamma, that means the local shear. So, that means this is corresponding to your phi m is corresponding to phi dash. Okay. and this is corresponding to phi. So, we have to calculate the bearing capacity factor corresponding to phi and phi dash both. So, this is corresponding to phi and this is corresponding to phi dash. Similarly, this is n gamma corresponding to phi, this is corresponding to phi dash, that is why it is n gamma dash, this is gamma dash. But we have the value corresponding to phi. If I take corresponding to phi value, which is given 35 degrees, then we are basically considering the local shear general shear failure case. And now, if you calculate the reduced phi and then calculate the bearing capacity factor, so that is our local shear failure consideration. So, that means, if I calculate the bearing capacity factor by considering phi, that will give us the general shear failure consideration, and if you calculate the bearing capacity factor considering the reduced phi or phi dash or phi m, that is the general shear failure consideration. But our case it is intermediate, so we have to interpolate this value. How we will interpolate? So, suppose we know for general shear failure it is 36 degree and local shear failure it is 29 degree, and for local shear consideration the value is, for example, this one is 12.7, and for general shear consideration corresponding to real phi. Okay, because you may ask that I have calculate the phi corresponding to calculate the bearing capacity factor corresponding to phi 35 degree, but I am writing 36 degree. Why? Because the phi that I am calculate that the bearing capacity factor that factors that I have calculated considering phi equal to 35 degree, actually that is the general shear failure consideration. So, that is why I am writing 36 degree, because that is the limit, and the bearing capacity factor that I have calculated considering the phi dash or reduced phi, that is the local shear failure consideration. So, that limit is 29 degree. So, that is why I am writing 29 degree. So, now this is 41.4. Okay. Now, we have to linearly interpolate this value, and our case is here, which is 35 degree. So, now we can interpolate these things, because this value is nothing but 41.4 minus 12.7. Okay. So, that is the thing, that means 12.7 plus 41.4 minus 12.7 into 35 minus 29, because this is 35. Okay, this is 35 minus 29 and this is 36 minus 29, the bigger side of the triangle. So, 36 minus 29, 35 minus 29. So, this way we can calculate the bearing capacity factor. So, this is for NQ bar, that means the linearly we have interpolated the value, and this is similar way we can calculate the N gamma bar. And then finally, we will use this bearing capacity factor in the equation, and I will get these values. Okay. So, this is the bearing capacity for the case when the phi value is in between the local shear failure and general shear failure, that means the intermediate case. So, that means here I have discussed what will happen, how we will calculate if the failure is local shear failure or intermediate. So, in the next class I will discuss that how these things can be incorporated in another way by considering the soil compressibility, because this local shear failure is basically the compressibility of the soil. So, that effect we can consider in our general bearing capacity equation, and then we can incorporate that effect that if the soil compressibility effect, if the soil is more compressible, then how, or the similar to the local shear failure, then how we can calculate that bearing capacity. So, next class I will discuss that compressibility effect and other effects. Thank you.